Good morning, everyone. This is Celso Batalha and Thermal Physics. That's chapter 10. And let's go to some of the basics of this chapter. We are going to pretty much define what temperature is, um, what thermometer is, basic laws of thermodynamics, in fact. I mean, we learned first law of Newton, second law. So thermodynamics has zero F law. I think they start 1, 2, 3, and then, oh, we forgot that one. Put a zero. So um, basically, I hope you all had experience before of if you have a cup of water and you want to chill up a little bit, what do? You put a little bit of ice there, and so once you do that, you know the water gets refresher and fresher and cooler. In Chile, that's very good, but also the ice itself is start to disappear. So what is happening here? So what happened is the water that it was hotter, was warmer, um, um, gives away something to the ice. The ice gets something and start changing. So the ice basically start melting. So let's see how this works in the universe of energy. So the unity of energy in thermodynamics is heat. Heat. So heat is energy, and energy is exchanged among objects. Like if you wake up and you step on a ceramic floor, you're gonna feel cold. Why is that? Because the ceramic floor has a very large capacity of, of sucking energy out of your foot, and then you feel cold, as opposed to carpet, right? The carpet it doesn't suck that energy out, so you feel good. You feel kind of okay. So let's go through these basic definitions, and let's start with the zeroth law of thermodynamics. That's the cool thing, and for that we need to define what thermometer is. Thermometer is an object. So if you have two objects, in fact, if you have two objects, one is warmer than the other. So and a kind of advancing concepts of temperature. But let's say both objects are not at the same temperature, which means they have different stored energy on them. And then when you bring them together and you allow them to be isolated, so what happens is there will be exchange of energy between those two objects to the point that eventually energy will be equalized. So how you have your water, you have your ice, and the deal is both ice and water will make a deal and try to get a common temperature. So perhaps the ice is going to give up so much, will absorb so much energy that it will completely, melt. And so now your mixing of water and ice will become a water that is somewhat a little bit cooler. Does that make sense? So that's the first one of the first principles of thermodynamics, and that's the so-called thermal equilibrium. Two objects are in thermal equilibrium when they are placed together and there is no more exchange of energy between them. So if that is true, we can think about thermometers. What thermometers are? Thermometers are not just this little piece of stick that has some mercury inside, and as you put in a hot environment, that mercury expands, which is true. But thermometer is anything that you place in contact with a some environment, and as you do that, both thermometer, which is your reference gauge, and the environment, they all reach a common temperature, right? And then so if you calibrate that thermometer, you can use that to establish temperature, basically. And then you take this thermometer and then you now stick to the other environment, and then you can compare and see if these two environments are at the same temperature or if they store equal quantities of energy. If they don't, when you place them together, they will exchange energy and will thermalize. Okay, that's one basic thing. So that brings to the zero law of thermodynamics. You take one thermometer and you measure material A, and you take the same thermometer, calibrate it the same way, and then you measure material B. When you place B and A together, there will be no exchange of energy between them. They are in equilibrium, and that is the so-called zeroth law of thermodynamics. Okay. Now let's temperature scale. So let's talk about Celsius. Celsius, the temperature scale, and we don't use a lot in the United States. It's very common in Europe, in Brazil, my country, and it's such that you use some instrument called thermometer that has a mercury in it, and it is calibrated in such a way that when there is a mixture of water and ice that reach the point of being equilibrium, so the ice is just melting, and if everything is in perfect isolation, so you bring your thermometer there, and then you can set the level of mercury that is reached as your 0 point. And then what you do now, you put another flask with water, and then you allow that water to evaporate, and then you have that bubbling going on constantly. And now you do the same exercise. You insert the mercury, the thermometer in there, and then you see the thermometer expands up to a certain level, and then you mark that level as 100. Okay, so then you have a scale. That's the Celsius scale, in which a thermometer in Celsius scale will mark the point of melting of a cube of ice as 0, and the point of vaporization of water as 100. Okay. So this thermometer depends on a material, mercury, but you can devise thermometers that really don't depend on which material you use to establish a scale. Like for the Celsius, we're using mercury, and that is the gas pressure type of thermometer. And the principle is kind of a simple. If you recall, let me bring something here. So when we studied before pressure, oh, that's a bad draw. Let me do it here. So let's say we have a cane. We have a point A, point B up there. That's the atmosphere, and there is a liquid of a certain height. This is point A. Then we can say that the pressure at point A is equal to pressure at point B plus the density of this liquid. So there is a liquid here, right? Could be water, could be mercury, whatever. The density of the liquid times G, which is our 9.8, times the height. That's how we relate pressure at different heights in a fluid, in liquid. So what we have here is something similar. It seems complicated, but in reality it's not. Try to follow me here on this. So you have a flask that has water, and you see that there is a nice mixing of water and ice, and supposedly got to the point ice is not melting anymore, water is not converted into ice anymore, so it's just perfect. Okay, and then you take a piece of glass that has a constant volume. See, the volume here is the same, it's constant, okay? And it's all communicated by this tube to this environment. Meaning the pressure you have here, this pressure, since the gas is the same pressure in there. Okay? The pressure is the same. Okay. So now what do you do now? Well, you say, okay, this liquid, if I had my mercury thermometer, I would insert it in there and I would read it 0, right? So here what you do, you take this gas and you immerse in this liquid, and then you wait for a while to have, you know, some thermal equilibrium to be reached between this liquid and whatever is inside this glass flask, and you ensure the temperature is the same. Okay, we've done that. So what do you do next? You take this ruler and then you move up and down so that 0 in your ruler is coinciding with this level. Okay, so follow me. So you have 0 here, and you have this level which happen to be at the same pressure of this gas right here, which is the same pressure of the gas right there. So this pressure is the pressure of this liquid at this level. Now look at this. Since we learned this before, this pressure here is the same as it is here, right? So the pressure here is the same pressure in here, and this pressure is equal to what? The atmospheric pressure, since this tube is open, times rho times g times h. So we can give and associate the pressure of this gas to this level, and we mark this h as a way to establish that pressure at 0 temperature. So what do you do next? Well, you take now, instead of having a mixing of water and ice, you have water boiling, and then you do the same exercise. So what's happening now? When you do the same exercise and you wait for thermalization, the pressure inside this flask is gonna have the same temperature. The gas inside the flask will have the same temperature as that of the boiling water, which is gonna be the same here. And then you're gonna 0 it, and now you're gonna have a different scale, H. So with this thermometer, you have H naught, which you can set, and you have H of 100 when you boil the water, and then any temperature or any other temperature of that liquid will set an H in between those two scales. Does that make sense? And then you have your. So in the lab we could do that. It's quite straightforward, but the main point is that depending on the type of liquid you have, could have mercury, could be water, could be something else, you always gonna have two points, one for 100, another for 0, and you can use any intermediate scale to which means any pressure, which is any intermediate scale, to figure out the temperature. Now one thing is that we find is that by extending these lines all the way to a temperature less than 0 in the Celsius scale, they all set a point that is the so-called absolute point, and then we can is as if the temperature is 0, as if you had frozen completely that material. But the main point is, wait a second, I have a crying dog here. Just a second. And that allows you to create this scale called Kelvin temperature scale, which is based in the 0 point, when you bring all the possible materials into an idealistic position in which they don't exchange energy anymore. They are all frozen. Relating Celsius with Kelvin is the simple expression. Temperature in Celsius is temperature in Kelvin minus 273.15. Okay, and yes, this is an equation you must know. There are other temperature scales. One is Fahrenheit, and see, I think I moved that one. And that is the temperature in Fahrenheit scale. Fahrenheit scale is such that you can relate that to Celsius as given this way. So, on Monday in the classroom, we are going to explore and do some problems on this with this scale. You just need to be on top of your mat. And the last thing in this chapter, I'm not going in 10.4 and 10.5, is expansion, thermal expansions of material. So if you have a rod that has, let's say, 1 meter size, and you warm up this rod, the rod will expand. It's not going to be just 1 meter size, but it's going to be 1 meter plus some fractions of millimeters, depending on how much you warm that up. And then it is found the ability of a material to expand depends on what that material is made of. Depends on which that material is made of. And we found that the expansion del L, so L naught is the original size of that rod, and L is to how much that rod was expanded, is equal to a coefficient that depends on the material times the initial size multiplied by the change, the temperature that was, the change in temperature that was given in order to allow for expansion. Here are the coefficients used in some exercise we're going to do in class. You can review them, in fact. And it is found that this is also true not only for linear type of expansion, but areal expansion and volume expansion. And the coefficients are such that expansion in area, the coefficient is 2 times as large as the coefficient, the linear coefficient, and volume expansion is 3 times as big as the linear expansion. Okay. There you go. So this is the expression for expansion in volume, and this coefficient beta is 3 times the linear coefficient. So basically in this chapter it is introduced the notion of thermal equilibrium. Is introduced what thermometers are, and you are going to be exposed to the notion of expansion, thermal expansion of materials. All right, and that's all she wrote.